Why don't I flinch? Because the laws of science differ fundamentally from all other. My face. Hi guys, welcome again to Science in 5. We're continuing with this idea of balanced forces. Okay. Now, in the previous video, we said if forces are balanced, it means they have got the same magnitude, but they're going in opposite directions. Okay. There could be more than two forces. There could be two forces. If the forces are more than two and the system is balanced, it means the forces pointing in one direction are cancelling out the forces pointing in the other direction. Okay. We've got a box of mass 40 kg lying on a table. Distinguish mass from weight. Okay. As we introduce this concept of forces, we need to try and make a distinction between mass and the weight. The word weight is often used in everyday language to ask a person's mass. How much do you weigh? 40 kgs. Imagine if somebody says to you, how much do you weigh? And then you say 255 newtons. Then be like, doo-doo. But technically, that's the correct answer, you know? Yeah. So mass is simply a measure of how much matter there is in an object. When we're discussing the mass or we're talking about the mass of an object, we're just saying how much matter is there in that object. Okay? And we measure mass in kilograms. We come to weight. Weight is a force different from mass. Weight is a force measured in newtons. Okay? And weight is actually a measure of the gravitational force a planetary-sized object exerts on an object. For example, myself, the last time I checked my mass, what was it? It was 95 kilograms. That's a lot. So my 95 kilogram mass, the earth pulls me down with a force. That force that the earth exerts on me is the weight. Okay, they're different. How are they different again? Well, if I was to travel to another part of the universe where I land on a different planet with a different gravitational strength, the weight that I would experience would be different. I would experience a different weight. But technically, my mass would remain the same, 95 kgs. Unless, of course, I'm one of those guys who eats 4 kgs of food or 6 kgs of food every meal, then my mass changes between meals. But no, I don't eat 4 kgs or 6 kgs of food in my meals. So my mass will remain the same when I get to that planet, new planet, but the weight, the downward pull that I'll experience will be different. So that's the difference between mass and weight. Very important as you begin to build a knowledge base on forces to understand the difference between mass and weight. So that one's done. We have to calculate the weight of the box. Now, calculation of weight is a very simple procedure if you know how to do it. Normally, we use the symbol F to represent force. And then underscore, we write small letters there to clarify what kind of force it is. Big F, force, little g, gravitational force. Weight. Okay. Later on, when we continue with physics, we'll try and marry the two, that the weight and the gravitational force from the planet should be the same. Okay. But for now, we use this to represent the weight of the object. It's equal to mg, which is the same as the mass times the gravitational pull or strength. So if we know the mass in kilograms times the gravitational pull, it will give us how much downward force you'd experience. So what is the mass? It's 40. 40 times What is the gravitational pull? Well, we're assuming that we're on Earth, so this should be 9.8. Okay, so now I need to grab my calculator quickly and say, what's 40 times 9.8? Okay, 40 multiplied by 9.8 gives me 392 newtons. So the mass is 40, the weight is 392 newtons. Unlike mass, forces always have directions in which they act. A force will always act in a certain direction. It's either pulling an object somewhere or pushing the object somewhere. This force is a pull force, it's pulling. Where is the box being pulled? In which direction? In the downward direction. Okay, so that's how you would calculate the weight of this object. Next, you're asked to determine the normal force. Now, balanced forces. One idea of balanced forces is that if forces are balanced, there is no visible effect that takes place. This box continues to lie on the table because the forces that are acting on it are balanced. Very interesting idea that every object that you see in nature has always got some kind of force that is acting on it, or forces that are acting on it. Okay? If you see that there is no visible effect that is happening, the box remains there for as long as ever, it means the forces that are acting on it are balanced. Okay. Now, how would I show these balanced forces? One way of doing that is to draw this diagram called a free body diagram. Now, what a free body diagram allows you to do is to take the object, make it into a dot. Say dot. Here is my object, dot. So the 40 kg is now the dot. I know that the force that's acting on the box is 392 newtons downwards. So I have this box being pulled down by a force of 392 newtons. And we say that force is actually the weight. Does this box fall down? No, the box remains where it is. So there must be another force that's balancing this weight. What is that force? The normal force. Okay, so the normal force is a contact force that acts between the box and the surface. So as soon as the box presses onto the surface pushes back. Okay, so the normal force is a reaction to the weight of the block. There's this guy called Newton. He spoke a lot about forces, and one of his laws, he says for every action, there's an equal and opposite reaction. If you push the wall pushes back. Assuming it's a strong enough rigid wall, okay? You push the wall pushes back. We call that an action-reaction pair. Action-reaction pairs are a type of balanced forces. In the case of this box, there is also an action-reaction pair. The box presses the table and the table pushes back. Okay. So what will be the force that the box experiences again from the table? It's going to be a force that balances. It's a force that balances the one going down. Now this one looks shorter than that one. So I'm going to manipulate my diagram to do like that. Okay. Now, what do you think will be the magnitude of this force? Let's call it force normal. Well, force normal must also be 392 newtons. Okay, so now I can say, oh, normal force is 392. Let me write it downwards. Is 392 newtons up. Okay, calculating the normal force is simple. What did I do? Drew a free body diagram. I looked at the free body diagram and I said, well, since these forces are balanced, the one force going down must balance the other force going up. What is the force going down? It's the weight. If I know the weight, technically, I can have an idea of what the normal force is, provided there are no other forces acting. So you can see this box, there are no other forces acting around it. So the weight and the normal force become a pair of balanced forces. The weight and the normal force become an action-reaction pair, and they're balanced. Since they are going to be balanced forces, if I know what the weight is, 392 newtons going down, the normal force will balance the weight and it will be 392 newtons up. So this idea of balanced forces, we use it a lot to solve problems. So that's it. That's it, guys. That's how you can calculate the normal force for objects that are on a surface like that. Just calculate the weight. The normal force will be the same as the weight. Again, just be aware, there are no other forces that will affect the downward pressing of the object. Okay, there are no other forces that will affect the downward pressing of the object. Sharp, sharp. Okay, that's it. That's how you can apply the concept of balanced forces to solve a problem like this. Especially 1.3, you needed to know how to use this idea of balanced forces. The weight calculation is a very simple calculation. Just remember the formula. Normally in a formula sheet, you should be given this formula, weight equals that. So if you see objects lying on the table, guys, it means the weight and the normal force have made an agreement. We will balance this object out. You can't pull the object downwards. You can't lift the object up. Remains as it is because of balanced forces. Balanced forces. Okay, balanced forces. All right, that's it with balanced forces. I think we would look at one more problem, but now I'm hoping you're getting it as well. I introduced again another idea of free body diagrams. We'll explore it in the next problem as well. Ciao. Bow.